Little late start, video watchers. Quiz yourself. Well, I guess it's too late, the answers are up there. So, so what kind of a series is this? It doesn't really look like either one of these, or it's like a combo of them or something. It's really weird and in the middle of both of these, especially with that N on top. So I want to talk about a test today that's going to help us. I wrote this and then didn't use it, but we'll get to it in a second. So I want to talk today about a really lovely test, the ratio test. What is awesome about this test is you don't have to have another series to compare to. So remember our other tests, we have the direct comparison, and we have the limit comparison. Bless you. Both of these need a comparison series, need a second series to compare to. And you have to have deep insight in a way. You have to be able to look at it and go, oh, it's like a P series with P equals 3, so I'm going to compare to that. And you may or may not get it right. This doesn't have another, this is completely self-contained within a completely self-contained test. So we're going to be given some series, and I'm going to be more and more not writing the indices. The implied thing is there's an infinity on top, and it starts somewhere, but it doesn't matter where it starts. It has no bearing where it starts, so we don't need to write it. We know it depends on n, and n's at infinity. So we're given this. We're going to compute this limit of the n plus first term to the nth term. And we're trying to see way out at the end of the series, what is is there a common ratio between the terms, like when we're way out there? And let me rewrite this in a way I think you're going to actually want to write this. So I would rewrite this like this for lots of reasons that you'll see today. And I did that with the LCT too, but especially here. It's really going to help. So given that, compute this. Then, if, notice how those are absolute values up there. So this thing will always be a non-negative quantity. If L is less than 1, then that means way out at the tail end of the series, to get from one to the next, you're kind of multiplying by a number that's less than 1. So let's think about what, let's make a little note here. This would mean that for large n, a sub n plus 1 is approximately L times a sub n. And we can think of this as like a common ratio. So they're kind of a geometric series way out at the end. Common ratio. So approximately geometric. And then we know that geometric series converge when that common ratio is less than 1. And that's really what we're doing. We're like saying, is this thing kind of geometric way out at the end? And if so, is this the common ratio? And if that is the case, then the series converges, and we're going to have a new term here, converges absolutely. Everything we've seen so far that converged absolutely because everything's been positive. But this allows for negative and positive things to be happening. So converges absolutely doesn't have as much meaning yet, but it will, especially next week. So let's just put a little quick definition. A series A sub n converges absolutely if you slap absolute values on it and keep adding it up, and that converges. So you're basically eliminating the chance that anything could cancel here. So, going to mean more. Not going to mean a lot yet this week, but it's going to mean a lot next week when we start looking at series that do alternate sign a lot. This is the test, it's beautiful. If L is bigger than 1, the series diverges. If L equals 1, we don't know anything. The test is inconclusive. And we'll have to try something else. Maybe one of our comparison tests, maybe a test we haven't seen yet. So this test, I'm going to recommend use the ratio test when you have moving exponents. In other words, the index appears as an exponent or factorials appear. That's the time to pull this test out. So I'm going to make a little tip here to use when the series involves factorials, the n factorial, and sometimes we're going to see weirder ones. We're going to see weirder ones today, or powers, with n as the power, or the index as the power. So this one is kind of like falling into line with what I'm saying, you know, when we should use this thing. So I see a power involving n, let's use it. So you say, you just want to be clear here, you say apply. We're going to go with this guy now. So we come in here, we're going to apply the ratio test. So I'm going to compute this limit. And here's the part that I want to give you some pointers on. So remember, this thing in here is going to be an plus 1 times 1 over a sub n. This means replace every n with n plus 1. So first I'm going to write that out. So this n becomes an n plus 1 plus 1. And then this becomes 3 to the 2 times quantity n plus 1. Check that out. Notice how I'm treating that n like it's, you know, a box that I'm just filling with n plus 1. And then times the reciprocal of the term as given. So here I'm just going to put 3 to the 2n over n plus 1. Then simplify and take the limit. Hopefully lots of stuff will simplify. And here that's definitely going to be the case. So we're going to simplify. And we're going to get limit as n goes to infinity of n plus 2. I'm going to break this apart in an interesting way, and you tell me if this makes sense. I'm just pulling the n plus 2 and the n plus 1 together. And then I'm going to pull this 3 stuff together, just so it help my brain just a little bit. And I'm going to simplify that exponent to be like that. Tell me if there's any questions or anything. Yes?
Why do we need it in the absolute value bars?
That's because, well, right now we don't, you're right. But in the future, we're going to have things that might alternate signs. So part of the LCT is to have those on there.
Okay.
Yes?
How did you get n plus 2 in the numerator there?
I took this n and replaced it with n plus 1.
Oh, okay,
So,
sorry.
yes,
So
that's okay.
I thought you were multiplying there.
Oh, no.
That's, yeah.
Good. Yes?
I was just confused on how you got like the with like the n plus 2 over n plus 1 and then
Oh, this is from here to here?
Yeah.
Cool. I will fix that up. So this is a product of fractions, so you can kind of think the tops are multiplied and the bottoms are multiplied. So I'm just rearranging this and moving this. See, it's really the same fraction. I've just rearranged to put the n plus 2 and the n plus 1 over each other. It's the same stuff multiplied.
Yeah.
Just for like help our minds like wrap. It seems like it did just the opposite for you, but other questions? Those are all great questions. Thumbs up. I'm getting the thumbs up. Secret thumbs up. All right, so we are at a math auction, and that was sold, so perfect. So now there's more simplifying that can happen here. Notice I can subtract these exponents. This one has an extra power of 2 at the bottom. I'm actually going to bring that out in front. So that's going to be 1 over 3 squared out in front, right? So do you see what's happening here? I'm canceling the exponents. the 3 to the 2n cancels out, and I'm left with 3 squared in the bottom. There's no n in that, so it might as well come out in front. And I'm left with this. Let me stop. Tell me if that looks cool. Or if there's anything that needs to be clarified.
So even though there's a +2 in the denominator, you can still take the 2n out?
Yes, because this, if you think about what this is 3 to the 2n times 3 squared.
Gotcha, okay.
Cool. What's that limit? 1/1, right? It's 1. Yeah?
Right.
We all believe that? I hope we believe that limit's 1. What's 1 billion plus 2 over 1 billion plus 1? 1-ish. So this thing goes to 1, and our final answer is 1/9. Does this series converge or not? Yes. Yes, because r is less than 1. So this is less than 1, so the series converges, and we'll just say absolutely to get used to saying that. And like Scotty noted, the absolute value didn't seem to do anything here, but we're going to say it anyway. By the ratio test. And there's all the proof anyone could ever want. Cool? Good? Your turn. Got my Yoda notes. So let's give you a good one. Oh shit, okay, well this is exciting. We probably ought to do this one together. You'll get enough practice in the web work with these factorials, but you probably have not done factorial work like we're about to do. Well, let's give some indices here. So, why not? So I see a factorial, and I remember what I said like 10 minutes ago, which is unusual for me. I forget a lot of stuff. But I do remember that I said when there's a factorial in there, apply the ratio test. So we're going to do that. So I'm going to compute L equals limit as n goes to infinity of a sub n plus 1. Now watch this, you gotta be real careful. I'm replacing the n with n plus 1, so I'm going to do that in parentheses. You can almost think as a good rule of thumb, replace every n with n plus 1 in parentheses and you'll be safe. Over 5 times n plus 1 times the reciprocal. Let me just give you a second. Now I'm going to simplify because that is the next step. So we got to be careful. Now this thing in here is in parentheses before I take the factorial. So what I've got there is 2n plus 2 factorial. And then this becomes 5n plus 5 plus 1, 5n plus 6, 5n plus 1, or 2n factorial. And at any point, just stop me and let me know if something needs clarification. Because this will be a little new. Okay. So I'm going to do that same move I did last time that Jaden and I were discussing. I'm just going to flip the bottom so that things are a little better organized. That's the only thing that's happening here is improved organization. My wife is always astounded that my math is so organized because I live like such a hobo. There's piles of shit everywhere. Just a hoarder. I'm a hoarder, really more than anything. My friend, my best friend, calls me a collector. It's very kind of. All right, so this we can't do anything with, but that we can if you see what's happening on the top, and let's actually make sure we see that. This is going to be one of the bigger challenges in using the ratio test, working with factorials. So that top thing, 2n factorial, means I've got 2n plus 2 times 2n plus 1. So remember how that works. You take this times 1 less than itself, times 1 less than that, times 1 less than that. So in other words, if I had 7 factorial, that is 7 factorial, 7 times 6 times 5 factorial. What I just wrote there is what I'm about to do here. And then this would just be 2n factorial. So check that out and truly understand what I've just done there. It's this, just with an arbitrary setup. And you'll be doing stuff like that. Sometimes it gets kind of weird, and you just kind of got to write it out and figure out what's happening. Can you finish this problem up for me, please?
I feel like the proof for this had to have been wild.
I can get it for you. I can do that. Get you the proof if you'd like. No. Okay. Okay. It was almost kind of like what I was intimating with geometric series stuff. It's a lot like what I was doing with that. So just much more organized and detailed, rigorous. Pick it up over here. You see those 2n factorials canceling? So that's really beautiful. And then we've just got 2n plus 2, 2n plus 1. And then this thing here, which was that, what's that, 5n plus 1 over 5n plus 6. Where's this piece going? 1, indeed. Right? Do you see that this piece is going to 1? Leading code, same power on top and bottom. When n is really big, 5 billion in 1 over 5 billion in 6. That's 1. So this goes to 1. Where does this go? Infinity. It blows up, right? It just keeps getting bigger and bigger. So this limit is infinity. That for sure is bigger than 1. So since L is bigger than 1 by like the most possible, the series diverges. Isn't that nice? It's just so, I just love the self-containedness of it. It's just right there, right? We don't have to move, we don't have to want things outside of ourselves. Let's do one more. I'll take questions on that too, of course. But, let's see, yeah. Okay, let's do this one. -1 to the n plus 1. So now we do need those absolute values because this series, let's actually write out what this series looks like. When n is 1, I've got -1 squared, which is 1 over 13. And then minus, it's going to flip sign every other time. -1 over 19 plus 1 over 25 minus plus forevermore. So you apply the ratio test. This one's not too bad. There's no factorials. Not super weird. Keep in mind that when you put the absolute values on, the -1 just goes away. Right? That can only change it plus or minus. And since we got absolute value, it doesn't matter if it's on there. So you can toss it away. If it were minus anything else to a power, that would be something we'd have to consider. We should be getting really good at taking limits like that, the ones that go to 1. Okay. Got a polynomial of the same degree on the top and bottom, leading coefficients are identical. What does that tell me?
Inconclusive.
Yep, don't tell me shit. That's right. DTS, DTMS, the official acronym. So, inconclusive. So the limit test are ratio test. That's what we're doing. Ratio test is inconclusive. We will see next Monday that this actually does converge. That does converge. It's called an alternating series, one that goes plus, minus, and there's a special test for that that's really simple. Yes, ma'am?
Why did the negative ones get tossed?
Because I got the absolute values on there, and so this -1 to any power is just plus or minus 1.
Right.
And so I've got a plus or minus 1 here, plus or minus 1 down here.
So it's just 1.
It just becomes 1. When you do the absolute value, you can toss away a -1, it becomes a 1.
Okay.
Does that make sense?
Oh yeah, because one. Okay.
There you go,
Gotcha.
solid, yeah. Cool. I think you might be ready to be free to to start the web work. Let's get on it. Does everybody know we don't meet Friday?
Yes.
Yes, that's why I have so much energy today. It's fantastic. So in that assignment, the first several problems are direct comparison, or those are just comparison tests, limit comparison or direct comparison. And then you'll see a problem that asks you about the basics of the ratio test. It just basically asks you the conditions for convergence. That tells you that the ratio test problems are starting from there on out. Let's give this a shot, and I'm here to consult. Gabe. Gabe, where are you, man? I am so yes. Here is yes. I just did it to like keep those above each other so the cancellation looked a little more obvious. That was all. It was just like for me, like kind of like a comfort move, you know? Yeah, makes sense. Does that make sense? Yeah. Thank you. Welcome. You got a pen too, right? Yes. Find you a chisel and stone. It's a pretty cool watch, Scotty.
Thank you.
I like that. What is that?
AirPods.
It's awesome. we won't know where the sum actually goes to. That's that's a harder question to answer, and we generally can't answer it. Is that what you're asking? I think. Good job getting the form of it. Nice. So what did you get here?
So eventually it goes to
Yeah,
and that one just goes to 1/3.
that's right.
It said 1/3. And since 1/3
Yeah.
converges, it does
Yeah,
converge.
converges. Think about,
It does converge.
yeah, think about the geometric series test. It's kind of the same thing, just in a generalized version of it. So we have that common ratio is less than 1 way out at the end. So it's like a convergent geometric
Yeah,
out
that's
there.
what I thought, but I don't know how to find the actual value of it on here.
Oh, wait, they do. Wait, let's check this out. I think it's because it's supposed to diverge. I thought it would, because we don't know how to get the sum of that. You're right. May I see your pencil really quick? Let's just go through your work and just check here really quick.
Or is it not too?
Oh, I think, so here's the problem. There's a 3 on top. That's it.
There is a 3.
So yeah, because that was 3. That you would change that into a times, or I think, or plus, and it's a times, because that's a 3n.
Oh, that is 3 times.
Yeah. So you get 1 and it's inconclusive.
Gotcha.
Does that make sense? Yeah, cool. Yeah. Whew. Yes, ma'am.
Okay, something like that.
Yeah, what? Yeah, I don't agree with that limit. How'd you get that limit? So, when n's a billion, what's a billion plus 7 over a billion plus 8? Is it 7/8? It's 1. There you go. Yes, ma'am.
Oh, cause I was thinking that,
Mhm.
okay, that's
You're doing
fine.
some weird ass stuff.
Yeah.
Now you're on track.
So in that case, if it's inconclusive, does that reach the sum of divergence?
No, you just don't know from this test. This
Do I have to
test.
do another test?
But no, you don't have to here. Here you only have to apply it, the ratio test. Oh, well, wait.
Yeah, cause it says,
Oh, shit. Oh, this isn't actually even the ratio test problems, right? Yeah, because the first ones are comparison.
Oh,
This
are
is
they?
this is a comparison test problem.
oh, I was
There
gonna
we
say, cause
go.
I feel like I didn't mean to use
That's
this.
Abraham, yeah, that first one, you can come up with a better answer for that. Let's take a look at that first one. Sophie, would you read me the series you had, please?
1/8 plus 1/15 plus 1/22.
Okay. Cool, so yeah, so do not use the ratio test until you actually see the thing that mentions the ratio test, and that signifies, now use the ratio test for the rest of these problems. So you have to convert this into a sum first, so let's see here. So 50. Looks like it's jumping up by multiples of 7 and starting at 1, and I think Sophie, you already had that, so yeah. So for this one, I would use let's see, how do we do this? Oh, limit comparison test. Use the limit comparison. So is this number 1? On number 1, use the limit comparison test. What would you compare this to? What does it look like? What looks like this? Yeah, and does that converge or diverge? That diverges, that's the harmonic. So do the limit comparison test with this series here, and you'll get a nice clear answer. The ratio test will end up inconclusive, and they ask you for something conclusive. Oh, it should converge, yeah. Let's see what you did here. Where'd that one come from? Oh, okay, gotcha. But you didn't copy the other, this is the piece that should be on the bottom then, because you used that end to get your one, and I agree with that. But that's the chunk that goes under.
Got it.
Does that make sense?
Thank you.
Cool. Let me give everybody a tip on that. Which one is that, Scotty?
3.
Number 3. On number 3, you're gonna end up having to deal with a limit, something kind of weird. So you have something like that. You get something like that, right, Scotty? It's like some weird root power event
Yeah, pretty
underneath
much.
it.
Yeah.
Yeah, something like that. So when you do this, this one should, you can think of this like, forget everything except the major powers. So this is approximately like the square root of n to the 10th. So this is square root of n to the 10th over square root of n to the 10th. Because that's really the dominant part underneath there. And that's just 1. And you can think of like, think a billion to the 10th plus 3 square root of that is going to be pretty close to this. So these two came into 1, but I feel like on this one, you should maybe be doing not the ratio test, right?
Okay.
Yeah, don't do the ratio test until it says ratio test, and then from there on out. On this one, I think, what was your original problem?
N over the square root of n to the 8 plus 7.
Okay, cool. So let's talk about that. This is going to be a comparison. I would use a limit comparison on this. But you have to think, what is the net effect? So n over square root of n to the 8th plus 7 is approximately n over the square root of n to the 8th. When n is large, that plus 7 doesn't matter. And that's n over the square root of n to the 4th. And that is 1 over n cubed. So that tells me that I want to compare to the p series with p equals 3.
Okay.
Yeah. So do limit comparison. This will be one of your comparators, and then your original series.
Okay.
I just wanted to make sure I have the right idea here. Like, I got it correct, I just wanna make sure that my process for doing that was right.
So now, the LCT doesn't have anything to do with 1. It just is, if this number is not 0, then
Oh,
they,
if it's not
then,
0.
yeah, exactly. The ratio test is the less than 1.
Oh, and then the LCT is.
LCT is just, if this is non-zero, they're the same.
But that was correct.
That is correct.
Do
Yes, ma'am.
anything else for that
Yes,
one?
absolutely.
Okay, I guess I was confused on the other one because it seemed like of a similar variety in terms of needing to use L'Hopital. Cause it was like,
Which one, I'm sorry, which?
cause when I did it as ratio. I got
Oh,
like,
yeah.
n plus 7 over n plus 8 or something
Yeah,
like that.
yeah.
What's the difference?
You were using the ratio test.
Right.
And that turned out to be inconclusive, right? Because that limit turned out to be 1. Here, if that limit had turned out to be 1, it would be okay because it's a different test.
Right,
So-
but how does the limit turn out to be 1 in that case, but not in this case? I guess.
This actually because you took the limit wrong.
Okay,
That's-
that's why I asked.
Yeah, because you're looking at the low thing. You did this on the last one. See?
Yeah, I did.
That should just be what, like a billion over a billion plus 7.
So it's just 1.
Yeah.
So then when does L'Hopital's come in?
Well, you could L'Hopital this right now because you've got infinity over infinity. So what's the derivative of the top with respect to n?
1.
1. And what's the derivative of the bottom with respect to n?
8. But just with respect to n, because that would also just be.
That's a constant though. That goes to 0.
Oh, that goes away, so it should be 1.
There you
That's
go.
why.
There you go.
That's why.
Now you feel good?
Yeah, I was
Okay,
just.
awesome. Okay, all right, solid.
So you did have to use L'Hopital though, it's just.
You did,
taking
yes,
it to
yes,
the
yes,
zero. Okay.
yes.
Okay.
I see your work? I feel like it's not one, actually, because I want this one for myself. So, so you're not actually, you're not taking the whole thing, you're just looking at the last part, but there's all the stuff that comes before it. So what, here, let me come around there. Come around and show you. Excuse me, Alex. Oh, shit, yeah, even if they were, we would have to like still take that into account, so like on that one, you can't, yeah, you have to keep everything. Well, I can just kind of tell you, so keep the product on the top and the bottom, and then replace that with n+1. And that'll actually take you to the next term that you would have. And do that on the top and the bottom. Do you want me to do one like this, kind of on the board? Yes, please. Okay, you got it. Which one is that point? 7? Let's see, on number 7. Crazy, it's a pretty crazy series, so let's see. I just want to make up something that's not. I just give me 1 sec to just like come up with something that's similar. Okay, so let's see. Cool. This is kind of like what you have, right? You're gonna want to see this eventually. I'm working on number 7. It's got a kind of a generalized factorial on it. It's a little weird, but it's definitely a ratio test because it's like a factorial. So when I crank out L for this, I'm gonna write, you gotta keep all the terms there. Oh, wait, sorry. Put in the n+1 minus 2, and then do this down here. Then, just the reciprocal of that. So that's like the setup there. Is that starting to, you start to see what's up? And then you realize that this simplifies to 2n plus 2, and this simplifies to 3n minus, or 3n plus 2, I guess, as well.
The top one is just 2n.
Oh yeah, it is, thank you. Yeah. But you want to think what came before these. So the one right before this would actually be 2n minus 2, and the one right before this is 3n minus 1. Yeah, exactly. Most everything cancels out except those last new terms.
complete setting up the, thing. It's a,
Oh, okay.
thing that I made a mistake, but.
Well, let's take a look. Okay, so, why it's cumbersome. So I agree with that. Oh, because you don't have a product in the bottom, so you actually just have the very last term. And you could probably like do some, or maybe you've already done the simplification to cancel things out. Is that what you did when you put those in there?
I simplified it at first, but I unsimplified it, assuming that that was what was making me upset.
That, so, no, so, let's take a look here.
Right.
Okay, yeah, we'll set up. So we've got 3n and factorial.
So, before we go any further,
Yeah.
why is it giving us like, all this information instead of just, like, why isn't it just telling us 6n plus 9?
Because it's not just 6n plus 9. It's actually the product of all the numbers leading up to that. So, for example, what this means is that when n equals 1, the bottom is just 15. So when n equals 1, this thing looks like this. 1 factorial. When n equals 2, it's 15 on the bottom times the next one when n equals 2. So plus another 6 times 21. 3 squared over 2 factorial.
So is that's some kind of factorial notation that we would have to?
No, this is really the best you can do to get that pattern out. This is the notation that describes the thing that they're trying to describe here
So
in
it's
the best way.
So how would I describe that when, describing
Okay, so-
that? Sure.
So let's look at the n plus first term. So you got all that there, that's quite right, except this part down here. We're going one term into the future. So we go all the way up to 6n plus 9, but then we go one more, because this is for n.
Hmm.
We go to, at 6n, so I'll put it in there. So this is the n plus first term. Then when I go and put the nth term in upside down, look at how you're gonna like this.
Oh, I see what's happening.
Do you see all that nice stuff canceling? Yeah.
Very cool.
You see? Yeah.
You're welcome.
Oh, that's fine. There's some good challenges in this problem set. We're gonna take this moment. Nobody's asking to run to the restroom. Be right back. It's okay, that's what I'm here for.
So, we're gonna go from here, so
Oh, you
these
did
all
great.
cancel out, but-
Yeah, dude. Yeah, let's see, let's double check, that sounds right. I'm good here. Is this good? Check it. Yeah, that's all good. I feel like there should only be one term. Sorry, it's okay. Let's see, so. Yeah, I think we got two. I think something canceled that you're not catching, so let's, so that's the problem. So on this one, notice how in front of this, what's in front of that? It's gonna be that, right? So there's a 5n minus 1 in front. So when this cancels
that
as
one
well,
cancels too,
so
so
that
that's
cancels, yeah.
So that's just 5n plus 4.
Correct. And then
Or is it
similarly,
1 over 5n plus 4?
it would be one, it would be, yeah, so it's on the bottom.
Okay.
Exactly. And then this
The
four, same
there.
thing, that kind of
So that's
cancels.
just 4n plus 3 over.
There you go.
Okay.
That's why, so now you've got a
So now
nice,
it's 4 plus 3 over 5 plus 4. That's just the end of it, okay. So
then the
that's-
limit of that.
And that's 4/5.
There you go.
So it's less than, so it's.
Beautiful.
Thank you.
Yeah, that's cool. And that's one of the like major tricks of this. So now you see that, you got it.
Okay, cool.
It still doesn't like my setup here. All right, well, let's take a look again.
So, this, I'm over here, this part.
Yeah. So yeah, so that's gonna be, yeah, that's gonna be the piece that's left in the bottom, everything else will cancel. And then we'll have that, And just so you, oh, wait, okay, I got it. I don't even know what that means, the domain doesn't match.
This town ain't big enough.
Let's try simplifying a little more, because we can't. So, you did that, and that was great. That and that simplify. What are you left with when you cancel those? 3 on top right, exactly. What about those?
You get, n plus 1, there you go.
So we can make this a lot simpler, and then if it complains, it has less reason to. Let's try that. Well, it should be actually fairly brief. Yes, yes, much less pain.
3 plus 1 over 6 plus 15. It would not shock me a ton.
It's not, what?
Oh, let me just very quickly.
Oh, there we go, yeah, yeah. There we go. Did it work? No. Okay. Let's take the absolute values off, so let's see, because we don't, well, I guess, well, it's supposed to be the ratio test, so it should be there theoretically.
I mean, that's what I suspected when it said something about a domain.
Yeah, I think that seems, there we go, okay, get rid of there.
Okay.
Sure. Okay, whatever, bro. Thank you. You're welcome.
Cam's that hand?
No.
Oh, okay.
Yes.
Yeah, there's some weird stuff going on. Yeah, let's chat. Let's see. So, so that's the right. That's great comparison. That's absolutely right. And then we bring that in here. I agree with all of this. What I don't agree with is what happens after that. So this is beautiful, right? But what we want to do is, notice that, what's the highest power in the top and bottom? 11. So that's gonna govern behavior out there. So it's the ratio of the 1 to the 1/683.
Okay.
But that should
That's
be,
just-
yeah, that's just, yeah, 1/1683.
Okay, so look for the highest power.
Yeah, exactly. Just look for the highest power, and if they're the same, it's just the ratio of those coefficients.
Okay, thank you.
You're welcome. Okay, I'm gonna sit down. Has anybody got questions? There we go. That's it. I could use the exercise, but
So for this one,
yes.
when you get to here, or well, one, is that right?
Yeah, let's check. Okay, so let's check it out. So we're here. So this, yeah, ratio test is gonna work great on this. And that looks beautiful. That looks great. That all looks really good.
Okay, so then I guess I'm just confused on where to go from.
Where to go from here? Yeah, so let me give you an example on the board, because we don't usually do limits like that, so that is a little weird. Which problem is that, Jade?
Number 4.
Okay, so let's see. So, it always helps to think about what happens when n is big. When n is really big, these don't matter. Does that sound reasonable?
Yes.
So you can think when n is really big, this is like that. And so you can get cancellation at that point.
Okay.
So that's 1/5. So I think that's maybe the best way to think about it.
Mhm.
Does that work for you?
Yeah.
Okay, cool. Okay, I'm faking me out. Good? Got anything you want to talk about? Okay, all right. I'm gonna trust you. You a good one? Oh, well. Bro. Nice. Doing good, Scotty? All right, awesome.
Can I talk to you after class?
Totally. Sounds good.
Thank you.
Busy.
You're busy?
Yeah. I'm trying to balance a little bit with assignments right now.
That's good. I was gonna ask you if you were doing okay.
Yeah, it's just, my dad's supposed to get out of the hospital on Friday,
Oh my God.
so,
Wow.
yeah, it's, I don't know, we'll see if he actually gets
but it sounds like he's getting stable.
Hopefully, I mean, he's on the same track that he was a week ago, and then this time last week he got really sick again, so we're just kinda walking on very thin ice, I guess.
That sucks. That
Yeah, a
just
little bit.
that just wears on you from
Yeah,
every direction.
yeah, and I mean, like, he had a great attitude, but he started being cooped up. So
Yeah,
it's
no
just
shit.
Watching him,
Yeah.
he's like, I wanna get out of here, and I'm like, I know, man, I don't know what to tell you, like, even.
Yeah.
So, you know, he's sticking with it though, it's just been busy, cause I go to see him every day, so it's back and forth.
Where's he at?
He's at Porter, it's right off Hampton and Broadway.
Oh, okay. Yeah, yeah. Okay.
So he's not too far,
That's good. It's
Yeah.
very good.
yeah, that's good.
But it's just like, yeah.
It's just rough timing with school,
Yeah, with what you're trying to accomplish.
So,
Yeah,
yeah, trying to keep up on assignments.
yeah. Yeah, but it's amazing what you're doing.
Well, thank you,
It is.
appreciate that. Yeah.
Noted and impressive. That one work out?
Oh, yeah.
Yeah, okay, you're moving on to bigger and better things. Cecil's got lots of green, so that looks good. You got anything you wanna talk about, or you good? Okay, you're always good. This is like perma good. See ya. And no class on Friday, don't forget. Darn.
Slam the door.
You good?
Yeah.
You're done. You're out.
Yeah.
You've had it. How are you doing?
Good.
You done
Just
too?
Just got 2 left.
Oh,
but
fantastic.
There's plenty of time.
There's so much freaking time. These class work days are good. I hope they make your lives better in general, that's the point.